Okay, so we're going to have the final session of today. So it's a double header, a joint presentation. We have Benjamin Brast-McKie and Miguel Buitrago. Ben was until recently the Stalnaker postdoc at MIT, and he has interests in logic and metaphysics and how they interact with AI. And Miguel is the lights going off and on again. Is a student at MIT in philosophy and linguistics and computer science as well. So he has many skills, and I think he's bringing a lot of programming expertise that we're going to see. So I think after this talk, he might be very busy with work requests. So over to you guys.
So yeah, I was very happy to get to work on this project with Miguel for 2 semesters during his UROP with me. And we've since developed it quite far. And so, yeah, I want to say a little bit to motivate this project. And I also want to give you a concrete example so that it's not just completely in the abstract. Okay, so this is a much simplified kind of description of the process that I found myself in, or at least a part of that process. It's a kind of idealization or simplification, but you have some language and you have some principles, some examples, maybe some counter examples. And then the goal is to develop a semantics or to modify a semantics in order to capture all of those. But then you have to, and this is the kind of pain point, this double arrow, this dotted arrow, you have to then explore its extension to see if the principles come out as valid. Okay, doing this once or twice is no big deal. But I found myself making little tweaks and then having to check the principles again and round and round and round. And that I just found this slow and tedious and prone to error. And sometimes I would do a good job and I would get to total clarity, but then a month or 2 would go by and I'd look back and have to kind of check everything again. And anyways, the goal is to automate, to shift the burden, the computational labor away from me onto my computer so that I can focus on doing the creative work. And the goal is to also make it easier to share work. So if you read someone else's paper, well, you're new to their system. It could be quite hard to work out all the proofs for yourself. Wouldn't it be nice if you could just go online and just type in whatever sentences you want inside their language and be able to check and see what counter models they generate very easily? I think it could also be very useful for students teaching these things to be able to see these models and for them to explore these models for themselves. So anyways, this is all I'm going to say for motivation. I do take some inspiration from the other sciences, physics and chemistry. And, many of these sciences are making great use of computers. And I feel like in logic, computer science indeed was born out of logic. And I feel like we should be reaping the harvest of our ancestors, right? This is the sort of thought. So anyways, and the time is right. Because there's a lot of talk about AI, of course. There's not as much talk about SMT solvers, so satisfiability modulo theory. These are very different. That they're SAT solvers. They're able to find you if you can describe some number of constraints to it in a language that it understands. It can tell you whether or not those constraints are all satisfiable. This is the kind of engine underneath this model checker. So the goal is it's a very general program. It's not just for the Truthmaker semantics. It could be for any semantics. But I think it's especially well motivated for Truthmaker semantics because Truthmaker semantics is complicated. And so I think, if you're just working with worlds, okay, there's still some complication you can get into. But I think it's in a way, it has a very natural motivation here. I think also Truthmaker semantics is still developing and, share, not everyone is on board as we are here. And so if it becomes easier for people to explore what these theories are and to see them demonstrated, that this could help promote the program. So this is kind of the spirit that led to this work. Okay, so I now want to, that's what I'm going to say so far about, for the motivation, I want to say, okay, what the alternative looks a little bit like. So I'm not going to go through all of this, but I've already said a little bit about the SAT solver. So we're using Z3. This was developed by Microsoft, but it's not novel. There are others, and I think we're in an era where developing SAT solvers will become, well, it already is a highly desirable thing to do. So these technologies are only going to get better. And so the thought is that instead of writing everything down, pen and paper, I mean, of course, we're going to do this too. This is not going to go away, but to also implement these theories. And I thought it would help just to show a little bit what this looks like. Okay, can you all see this? Okay, so we've seen some of the definitions a few times, but I just want to show, you can think of this as a kind of change of notation. We have here verify, and I'm specifying its type. I'm giving it a name, so verify, and it takes a state. So this is going to be a bit vector. Say a little bit more about that. And it's going to take a sentence letter as those are the first two inputs, and it's going to give out a truth value. So this is a bool sort. Okay, so this is what it looks like to specify a primitive inside this framework. Okay, why bit vectors? This was kind of the impetus for the using Z3 to begin with, is that Z3 knows, so it has various theories that it knows about, so like inequalities or integers, those kinds of things, but also knows about bit vectors. So here's a bit vector. It's just a sequence of ones and zeros. So this is going to be a bit vector for n equals 3. Oh yeah, thank you. That's great. And you know, there are going to be others. So you have, okay, so for bit vectors of length 3, these are going to be the 3 atomics, and then they're going to have fusions where you put them together. So if we put the bottom 2 together, we'll get, you know, this and so on. So the theory of bit vectors that Z3 already knows about gives me finite. It's going to be a finite state space, but we can use these atomic bit vectors to model states. So this is like, you know, if we only have 3 atomic states, then we have all their various fusions and whatnot. And so this was the kind of key insight to led me to see that I could use Z3 to build up a state space using bit vectors, and that's the role that they're playing here. So that's why, you know, we have bit vec sort coming here, and then atom sort is the atomic sentence, and bool sort is the truth value. So okay, so this is verify. You can see possibly is the same sort of thing, except now we don't have atom sort. It's just a one place predicate. So assigning a truth value to a bit vector. Okay, and then once you give yourself some number of primitives, you can start to write frame constraints. So that's what this one is. This is this downward closed definition we've seen a few times. So you're saying for all x and y, where x and y, these are defined to both be bit vectors. So states, these x and y are both states. So for all x and y, if x is a part of y, so we have that here, y is possible, then indeed x has to be possible. Okay, so this gives you some sense of it's the same game, just a new notation. Okay, so here's an example where the premises are negation A box or diamond right C. So this is if A were the case, C might be the case, and then we have box right. So these are our premises, and the conclusion. This is kind of like strengthening the antecedent, just with some additions to the premises. Okay, so you want to know, is there a counter model? So it builds a state space for you. And it tells you which ones are worlds, so these maximal elements, and which ones are possible. And you can have it print the impossible states too, but I often choose for it to not do that. So that's a setting you can turn on and off, whether it prints the impossible states. And it interprets the imposition relation, and that's also constrained. So this is, and it gives us, and then it uses this to interpret all the sentences. So this is a bilateral semantic, so it's going to tell you what the verifiers are first, and then followed by the falsifiers. Okay, and what it's trying to do is trying to make all the premises true and the conclusion false. And if you don't like sort of the model that it happens to find on the first go, then there's an iterate function. So you can then say, okay, find me 3 counter models. So you can start to like sort through and sort of get some sort of sense of what at least the minimal counter models are. So it's always looking for minimal counter models. So they might not be the most natural. And this is partly why I've kind of added more premises, just to kind of make it a little bit more natural. But it gives you, yeah, so anyways. But sometimes it won't find any counter models at all. So right now we're just searching for atomic states, only 4. So it's a pretty small finite space. And so it's surveyed this entire space and says there are no counter models to this. If A or B were the case, C would be the case. Conclusion, if A were the case, C would be the case. Okay, so this comes out as valid, at least over this very small space. Okay, so this is just to give you some sense of what it looks like. And there are some limits. So as you increase n to more and more atomic states, of course, it's going to get harder and harder for it to survey this space. And so this provides some new pressures on what counts as a theoretical virtue. And I think this is comparable to the kind of considerations we already have in developing theories. You want them to be something that you can countenance and use and think with. Now it's just that we want to extend those considerations to the tools we're using. So I'm going to hand it over to Miguel, who's going to talk a little bit about all of that.
Hello. Yes. Now that we have a computer, it's important to think about, like the space of things we're actually saving on here. Because, when we're on paper, we can write infinity, or we can write like 1,000,000 on paper, and it doesn't really matter. But, if we're storing 1,000,000 things, or God forbid, an infinite amount of things on a computer, you have to think about the space. So now that we have a state space and we're dealing with finite state spaces, we might want to consider if we ever store any data structures that have all of the state space in them, or use the entire state space. If we ever do have structures like in the computational architecture somewhere that do use all the state space in some sort of way, then as n gets big, because n is the number of atomic states, the state space will grow exponentially because it's 2 to the n. So the state space gets big really fast. So you may be, given that I'm talking about this, we do actually have this sort of data structure, namely primitive functions. So for example, consider the primitive function for Professor Fine's imposition semantics, the imposition relation. The imposition relation takes 3 states. So its inputs are in, could you switch really quick to the handout?
Oh, yeah.
There we go. Yes, here. Okay. So we see here that just a couple of examples of some functions. If you look at the 3 bullet points in the middle. So imposition has inputs in B, where B is the space of bit vectors or states. I really should have said states. Sorry. And it outputs them into true and false. As n grows, this is going to take a lot of space. And we can make that more precise with a notion called space complexity in computer science, which is measured or, written with this big O notation, which is what you're seeing there. Basically, we see that it grows exponentially. And that's important for two reasons. First is time. So assuming that this data structure Z3 is going to compute, and we actually do know that Z3 is going to compute this data structure, because if we look at, so primitive functions. There is imposition. That is how Z3 saves the imposition relation on the back end. So part of the model checker is showing the porcelain so we can hide all the ugly plumbing, and that's an example of ugly plumbing that we're hiding. So as you see here, like it's basically saving every single combination of three when it's true that it's the three are in an imposition relation, and then at the end it just says else false. So in the worst case, it's going to save something for all 2 to the 3n inputs. So in the worst case, it's basically an array, which means that if we want to calculate the entire space b cubed, the imposition relation for it, in the worst case, that'll be 2 to the 3n things you got to save. And if you're saving 2 to the 3n things, that's going to run in quite a long time. But it also means that since it's going to run in quite a long time, then the size of n that you can go to is rather small. All right. So computational complexity matters for two reasons. First is runtime. You'd rather take half a second than a second. But also because the higher n you have for theorems, the higher security you have, the higher confidence you have that is in fact a theorem. And it's not just like that there's no counter models up to, for example, n equals 3, right? Okay. So can we go back to the... Okay, so to make it a little bit more concrete, if we take, for example, n equals 5, and we consider a semantics like finds and position semantics, we can try to think of the amount of like operations that it would take to fill up these arrays. So for verify, the space it's in is in L, where L is a set of atomic sentences in the example. So for example, if our theorem is A box right B, conclusion B, L would be of size 2 with just A and B in it. So the space complexity of that would be O of the absolute value of L, absolute value of B, which is, in this case, 2 times 2. If we set n equal to 5, 2 to the 5th, which is 32 times 2, 64. 64 operations, that's nothing for a computer like this. But now consider the imposition relation. Imagine it has to fill, in the worst case, everything, or like a good proportion of it. N equals 5, 3 times 5 is 15, 2 to the 15th is a really big number, Okay, so there you can see how the computation starts to matter, because filling up something that's 2 to the 15th or some proportion of it is going to take a long time. And it basically means that we cannot have like theories that have primitives that need to fill up all that space are going to take quite a bit of time. Basically what this all means is that we need to consider now the arity of our primitives, especially if they take in things in the state space. So it becomes a theoretical virtue to think about the computational complexity of our theories. In this case, theory with primitives of less arity is more virtuous because it's faster to compute, and we can actually compute it for higher n more reliably than a theory with primitives with lower arity. Okay. Should I talk about logos? Sure. Okay. So Ben will talk about this in a sec also, but he developed a version of finds imposition semantics that basically does not need the imposition relation, does not need this three-place relation. And the computational difference between that theory and the imposition theory is quite significant. For example, for many of the things that are theorems, so in other words, no counter models found, the imposition theory is about 10 times slower, so about 0.01 seconds versus 0.1 seconds, or in some cases 0.1 seconds to 1 second, when n is set to 4. So when the state space has 4 atomic states, and when n is set to 5, if you let the imposition semantics run for 100 seconds on many of these, it will not finish. But with the imposition minus imposition version of the theory, it does finish for, I think, at least most of them. So there is significant cost, because like a theory with a primitive of arity 3, which is essentially the only difference between these two theories, tops out at about 100 seconds. We're not going to wait 100 seconds for a large amount of theorems. When we can develop a version that does not have a primitive that has such a computational burden. So we can think of like this sort of virtue, kind of similar to how like simplicity is often a virtue in theorizing. Like, intuitive simplicity is something that's intuitively simple is better than something that's not intuitively simple. It's often hard to measure though. But computational complexity gives an objective measure of simplicity in the sense that if you have a theory that is easier to compute and easier to work with the tools you're given, in this case, the tool is the model checker, then that is more simple and more virtuous in that sense than a theory that uses, primitives of hierarchy in this case that are more computationally burdensome. And it's also objective and easy to measure. So good in that sense.
Great. Yeah, thanks so much. All right. Okay, great. So I want to say a few more things. I guess one is just what is the relationship between these two theories? So Miguel mentioned logos, which is I'm trying to build a unified language with many operators in it, and I want it to be modular, so something that is kind of easily extensible. So usually the way it goes is you choose your language, and then you define the models for that language. You have your recursive semantic theory, and then if you want to add new operators, you kind of have to start at the beginning again, and you can make use of what you had before. But I wanted something that would be very collaborative, something that people could develop their operators and then import them as they needed to. And there's a nice example here. Great. Okay, so we looked at this logo semantics here, and to define imposition, the only difference, so what we're going to do is we're going to import the logo semantics, so we just have that, and we're now just adding pieces to it. Okay, so the only difference with this, so yeah, given that you have basically the standard state semantics set up inside logos, then if you want to add an imposition operator, that's all that this semantics does. And so here we have the imposition operator. You can see the 3 bit vectors that Miguel talked about. And then here's the constraints on them. So this is, we just saw before, we have inclusion, actuality, incorporation, completeness. So these constraints, these frame constraints on this imposition relation. Okay, but I realized that, so I came to this sort of in a roundabout way, but I realized that this was not entirely necessary, that there is a way to kind of just define an imposition relation just directly, instead of taking it to be primitive. And just to give you some sense of how that goes. So here we define what it is to be a world. It has to be possible and maximal. Possible is a primitive, maximal is not. Maximal is defined up here. Okay. And the innovation is this idea. So actually it might be easiest if okay, so there's this idea of a compatible part. So S is a T compatible part of some W, meaning it's a part of W and it's compatible with T. Okay, then you can look at the maximal T compatible parts of W. That's what this next definition is. So given W, you're going to get potentially many maximal T compatible parts of W. And then we can define imposition, or something maybe not exactly the same as imposition, but somewhat stronger than imposition, as well. It requires you to be a world. This is just for the completeness sake of the completeness constraint. And then what it does is it says, okay, there has to be some maximal T compatible part of W where T, the state you're imposing, together with that maximal T compatible part, their fusion is a part of this world U. And so this is, I refer to these types of worlds as alternatives. And you can think of them as like making a minimal change, right? They're leaving as much of the original W behind as you can while imposing T onto it.
So what we're going through right now is a series of files where there is a whole bunch of examples, and the examples are formatted like premises and then a conclusion, and there's a series of settings for that given example. For example, how big n is, how big you want your state space to be, whether you want the example I ran had like all the ugly Z3 things print out. You can turn that on or off. Usually you want it off, but if you want to scare people like I did, you turn it on. There's also a setting to compare two different theories. There's a setting to plenty of other settings. So we're adding them as we see them useful. And it's just like a big file with like 30, 40 different examples. You can kind of see some of them commented out right there while this is loading.
Once you figure out you find some counter models that you like, or you find some theorems that you also like, and you think, these are good, I want to hold on to these. Well, you can turn them into unit tests. So they're just a whole stock of tests. And so as you make tweaks to your theory, you can then just run all the unit tests. And that's what I would like to do.
So it took less than a second to make a counter model, which is dreamable for a human. Yeah. I mean, there's definitely a job to be. I mean, so Ben had a seminar last semester where we used the model checker at the end. And that was my first exposure to Truthmaker Semantics. Well, I mean, besides this project, that was my first exposure, like doing proofs by hand in Truthmaker Semantics. So we had to do that first. I experienced the pain. And then he had us interpret the models. So there still is a role for interpreting the models, obviously. When you make a counter model, they're usually interpretable. Like a human-made counter model is usually interpretable. These, though, like Ben said, are minimal. So they're usually not always interpretable or easy to interpret. So there still is definitely a task for, traditional model theory, definitely, like in all regards.
Okay, so sorry, a little flustered with all the counterexamples, but yeah, I guess the hope is that, I found this to be a really nice process for myself. I know it's extremely slow and laggy up here, but it's just immediate, and you can make little tweaks to the theory. You can see what the differences are. One thing I wanted to demonstrate was what happens when, so I included these various, okay, so this first one that we looked at is somewhat reasonable. But yeah, if you look at just, okay, so yeah, here's, okay, so one thing to see here, so this is on this logos theory where it has been defined, and you can see that there are some alternative worlds. So this is where you, oh no. Oh God. I don't know. I guess this is the price of, I don't know. Technology is sometimes like this. But yeah, maybe I'll just describe what the point is that because the imposition relation is primitive, it's very easy to find minimal models where there's just very few relations. So you can end up with these kind of trivial situations where there's just no A alternatives because it's found the minimal model. And even though it satisfies all the constraints, it's not that meaningful of a minimal model. And it's nice that this doesn't face that. So it's finding minimal models, and indeed there are A alternatives, which is quite nice. And so I don't know if it will let me, but I'm going to try. Okay, so this is what it looks like with where we just have negation of A, and then if A is the case, then C is the case. And you can see, oh wait, is this one? Oh, it's still loading. Yeah, it's on my computer, but not on that one. Yeah.
I will say as a plug, it's slow not because of the program, it's slow because of Zoom. So trust.
Oh, really? Oh, really? I see, yeah. Okay. All right, well, that's good. All right, well, maybe oh yeah, here we go. So you can see that A alternatives to B is just this empty set. And this is actually true for almost all of the many of the counterexamples on this imposition theory, where imposition is primitive, just because it's very easy to make the extension of imposition very small. Okay, well, I don't know. Do you have anything else you want to say? I'd be curious I'm very happy to answer questions. I know it's a little bit muddled with the technological difficulties, but yeah, happy to answer any questions if you guys have it. Yeah.